Hello dear learners, welcome back. In today's video, today we are going to see a continuous beam with a sinking effect. So in this problem you can see there is a continuous beam AB, BC and CD imposed with the given loading having the different values of the moment of inertia, and here one specific condition has been identified, that is joint B is going to sink by 10 millimeter. The value of E and I are already given into the problem. So as usual, the very first step is to find out the fixed moment. So take the various individual spans AB, BC and CD and putting the appropriate value, or first of all we have to select a case UDL, first span UDL throughout the length. So the fixed moment will be WL square by 12. Put the values of a loading and the spans and get a value of fixed moment. So here you can see in the first step we have already worked out the various fixed moments for the various span AB, BC and CD. Next is to identify the boundary condition depending upon the various displacements which shall occur into this particular problem. So first, related to the support condition, that is fixicity is available at point A and at point D. So we know about fixicity, the slopes are equal to 0. So that is why here theta A is equal to 0 and theta D is equal to 0. As far as the another is concerned, that is deflection is going to take place, or the sinking of effect is going to take place about point B. So here you can see delta for span AB and for span BC is equal to 5 millimeter. Is it okay? So these are the boundary condition which are available in this particular problem, and all these various things are to be utilized in the governing equation. So here next thing is to understand the equilibrium of a whole beam. So here you can see about a joint B, it has to be in the equilibrium, and when it will be in equilibrium, when final fixed moment, that is MBA plus MBC should be equal to 0. Similarly about point C, MCB plus MCD is equal to 0. So these are the various presets required for analyzing this particular continuous beam by the slope deflection method. Is it okay? So let us move ahead and do the further analysis. So here you can see I have enumerated the various boundary conditions. Now it's time to apply the governing equation of a slope deflection one by one. So take the first span AB, show all the probable rotations and their induced moment due to the rotations. So and here I have to simply add on all these about an individual joint A and then joint about point joint B, so that we will be having the construction of the governing equation of slope deflection. So here you can see MAB, and this particular is a governing equation applicable for span AB. Is it okay? So here I am putting the value of MAB. Here as far as theta A and theta B is concerned, theta A is equal to 0 because it is fixed, theta B is going to occur because it is continuous and it is going to rotate about point B. As far as this delta is concerned, yes, delta is going to occur, and that is value is given equal to 5 millimeter. So put all the various boundary conditions and the various known values in this governing equation, and simplifying it, you will be getting a value of MAB is equal to 1600 theta B minus 14, calling it as equation number 1. As far as the sign conventions for the slopes and the deflections are concerned, or sinkings are concerned, that are been understood from this various diagram. Is it okay? So here anti-clockwise at both the ends, so it was minus, and here it is plus because they are clockwise. So this has been already explained into the earlier slide, and especially into the introduction of the slope deflection method. Now after finishing with this span AB, let us move to the next span, that is MBA, fixed moment about point B, that is MBA. And here again what we did, whatever already we had MAB, fixed moment about point B, so we have substituted the value theta B and theta B, theta B and theta A value also we already know. We have substituted that, and again it is going to be minus 6 EI delta. So this is what is the equation number 2 for that span AB, MAB and MBA already found out by equation number 1 and 2. Similarly for equation number for the span BC, so all the various probabilities are being shown here and the governing equation is available. Putting the boundary conditions and the known value of the sinking of the support, we are going to get a new equation MBC is equal to this much. Is it okay? So MBC span and MBC has been found out. Now next is MCB. Again doing the same, put the value of theta B, theta C and delta CB. So here again you can see I have got a new equation number 4. Then I will be selecting another span CD, again a governing equation, putting the boundary conditions and the available value of the delta, and this is how we got this particular equation number 5. So here delta is coming out to be equal to 0. If you remember A, B and C, B was sinking. As far as no sinking effect is going to be occurring into the span CD. That sinking was only valid for A, B and BC. So in C, this term is coming out to be equal to 0. So this is the only new thing which we can see into this governing equation. So here you got a value of theta C and theta D as a boundary condition. Putting that into the above governing equation, we got equation number 5 for MCD. Similarly for MDC. So you can have this look at this equation number 6. So putting the boundary condition and the value of delta for that individual span, and we got equation number 6. So right now we have got various 6 equations which are in terms of the deflection or the value of delta and the slopes occurring at point A, B and C. Is it okay? So all these are been shown once again so that we can understand what is to be done with this particular equations. Is it okay? So here MAB and all these 6 equations which we have already formed are being enumerated here, and all these are to be used for the further step, that is the application of a equilibrium condition about that individual joint. So about point B we have this. So about point B this is equal to 0. Then about point C this is going to be equation number B. So on solving equation number A and equation number B, which has only 2 unknowns, theta B, theta C, theta B and theta C. So 2 equations, 2 unknowns, solve them simultaneously and get a value of theta B and theta C. So after getting this value of theta B and theta C, which has always occurred into equation number 1 to equation number 6, so simply substituting this value of theta B and theta C in equation number 1 to 6, you will be able to get a value of the final moment for that individual span. So here you can see the values of theta B and theta C and equation number 1 to equation number 6. So selecting one by one equation and putting the value of theta B and theta C, you will be directly getting the value of the final moment occurring for that individual span. So here equation number 1, put those values. So MAB is equal to minus 16.528. From equation number 2 we got MBA. From equation number 3 MBC, then MCB, then MCD and MDC. So these are the various, whatever is been shown into the maroon color, that is a final moment occurring for that continuous being after taking into account all the probable and the given displacement for this particular case. Is it okay? So we have obtained the result for the final moments which are to be drawn into a diagram, which we call it as a final fixed moment diagram. So I have constructed that final fixed moment diagram by plotting these as the ordinates for that particular diagram. Next, free bending moment diagram. Consider an individual span. Its free bending moment value we know. Put the values of intensity of a load and a span. we got this particular free bending moment diagram. Is it okay? After that we have to superimpose these two diagrams, and after superimposing, red line is going to be the neutral axis, means about this is going to be the positive bending moment whose value is to be found out. Is it okay? So after finding out the ordinate for the final moment about this particular thing from this about this point, so difference between these two is going to give you the resultant moment acting for that particular span. So this is what we have to understand whenever there will be the sinking effect occurring for that particular sort of a continuous beam. So I hope you all are getting what are the chronological steps to be understood and to be applied for the analysis of a continuous beam by the application of slope deflection. With this, I conclude the analysis of the continuous beam by the slope deflection method. I hope you all have got what are the various procedures to be adopted when which sort of a problem is to be analyzed. So thank you very much for watching this video, and see you in the next part of structural analysis.